Hello everyone, I am Sommer and I am happy to present our work on the detection of different levels of primitives in 3D point clouds, namely planes, their intersection lines, and corners. I am a PhD student in the Computer Vision group at the Technical University of Munich. This is a joint work between Stanford and TUM, which was conducted together with Yumin Sun, Leonidas Guibas, Daniel Cremers, and Tolga Birdal. Our everyday environments are composed of a huge number of man-made structures. They usually involve a large portion of planar primitive forms which are either parallel or orthogonal to each other. This renders the issue of discovering orthogonality relations in 3D a vital task for low-level vision algorithms. In this video, we propose a geometric, voting-driven method to jointly detect pairs of orthogonal planes in oriented 3D point clouds. Let me start by giving a quick overview of what we are actually doing. The input to our algorithm is an oriented point cloud, meaning that we have a set of points in R3 together with normals. Note that while we do need the orientation of these points, so the normals, they do not need to be consistently oriented, so there is no notion of inside or outside the object. In a first step, we detect pairs of planes that are mutually orthogonal and build a relationship graph from the detected pairs of planes. These are then clustered in order to remove duplicates. The clustering is a very important step in the algorithm pipeline, as our approach is semi-global and thus will always produce duplicate candidates by design. Once planes are clustered, we propose two different ways to proceed further. First, we can extract corners, which correspond to triangles in the relationship graph. We can refine the 6D position of these corners to a higher resolution than that of the input point cloud, so the result does not have to coincide with one of the input points. The second path we can follow is to reduce the graph in order to find sets of parallel planes in addition to the orthogonality relations. Optimizing the parameters of the reduced graph in the end produces a planar abstraction of the point cloud, which can be useful in particular for indoor environments with very regular structures. Let's start with the first module of our algorithm, the plane pair detection. In our work, we are using a concept called semi-global Hough voting. It uses point pairs for which it looks at pairwise relations. If we take a look at the point cloud here, we can, for example, pick the point pair x1 and x2 with their respective normals. Now, assuming each of the 2 points lie on a plane, we know that the 2 planes are orthogonal if the scalar product of their normals is 0, or, in the case of noise, sufficiently small. We can establish more relations between the 2 points by looking at the vector d connecting them. We define a feature vector f whose components are the scalar product of the 2 normals, the projection of d onto n1 and n2, and the length of d. Note the similarity of this feature vector to the original point pair features defined by Drost et al. In their work from 2010. Let me now explain the term semi-global voting. Instead of having one global Hough voting table in which we cast votes for each candidate, we set up a new voting table for each reference point x1. Then we pair this point with a set of x2s and cast votes. For each x1, we extract the candidate which has most votes. So, what parameters do we actually vote for? If we already assume that point x1 is part of a plane, and we want to find a partner plane orthogonal to this first one, we actually only have 2 degrees of freedom. One is the direction of the normal of the second plane. The plane can rotate freely, but always has to be orthogonal to the first plane. We call the according parameter theta. The second one is the distance of the second plane to some characteristic point on the first plane. As characteristic point, we choose x1 and call the parameter rho. Note that setting up one voting table for each x1 allows us to reduce the dimensionality of the problem from 5 to 2. In order to ensure that x1 is really part of a plane, we also cast votes for points that lie on the same plane. A plane pair candidate is then only accepted if these votes are also enough. Each candidate plane pair is inserted into a graph, where the nodes of the graph are planes, and they are connected by an edge if they are orthogonal. In the end, this means that at the beginning we have a very disconnected graph, so we cluster graph nodes to obtain a more connected graph. After clustering, as mentioned previously, we propose two options to proceed: corner extraction and graph reduction. I will start by explaining the first one. Let's quickly go back to the graph. As every node in the graph is a plane and edges denote orthogonality, it is easy to see that triangles in the graph correspond to corners in the point cloud. On the right-hand side, you can see an example of a plane graph overlaid on real colored point cloud data. We extract such triangles from the graph and store for each corner the three plane normals and distances, in total yielding a 6D SE3 local reference frame. To refine the corner positions, we aggregate the three normals in a rotation matrix R and the distances to the origin in a vector D. Then we minimize a sum of squares energy, which assigns each point in a neighborhood of the corner location the distance to its closest plane. This way, we get very accurate corner positions, as you can see in the figures on the right-hand side. The second path we can follow in our pipeline is graph reduction, followed by a multiplane refinement. Let us have a quick look at this option. After clustering the graph, we might encounter adjacent triangles in the final graph. The non-adjacent nodes in these adjacent triangles, here marked in orange, then must be parallel. We exploit this fact to construct a reduced graph, where nodes are collapsed if they have parallel normals, and each node gets a list of distances, similar to the graph reduction in globfit. Doing this, we can define an energy over the reduced graph, which assigns each point in the point cloud the distance to its closest plane. However, this energy still lacks the notion of orthogonality between planes, so we need to introduce a coupling or regularization energy that penalizes the deviations from orthogonality. Our total energy then is a weighted sum of the data term and this regularization term. In the actual optimization, we use an unmanifold parameterization of the unit sphere elements Nk and add a robust M estimator to the data term to handle outliers. In this talk, we focus on visual results. For information on the used datasets and our choice of parameters, we refer to the paper. There you can also find more quantitative results, tables and plots. We start with a visualization of plane pairs that are not yet clustered or refined. We represent one plane pair by its line of intersection. One can see that due to discretization artifacts of the voting process, the detections are not very accurate. Furthermore, the localized voting leads to many duplicate detections. After clustering, the picture looks much cleaner. We only have one line per plane pair left, as expected. However, parameter accuracy is still not great. Lastly, we show the final results of our algorithm. The pink lines are intersection of planes after optimizing the reduced graph, while the red, green and blue local reference frames denote the extracted and refined corners. Now we show a video that demonstrates the robustness of our corner detection. You can see the detected corners in a sequence of depth images. Note that we are not tracking the corner, but redetecting it in every single frame. Here you can see 6 depth images from a video sequence, which are not yet aligned or registered. We detected corners in each of the scans and just by aligning the corners, obtained a coarse auto-alignment of the depth scans. Such a coarse corner-based alignment can be used as initialization for any other scan registration algorithm. In summary, our method provides a voting scheme to detect pairs of orthogonal planes, which can be used to extract super-resolved corners from point clouds and to create planar scene abstractions together with parallelity and orthogonality relations. For anyone who's interested in more details of our work, you can check out the code on GitHub. We also included pseudocode for the major components of our method to simplify basic understanding. Thank you for your interest in our work.